Hello, this is Ethan Lowry, and today I'm going to be talking to you about the Closed Loop Control Lab with the help of Brandon Schroeder, Dan Gaucha, and Kyle Martin. First thing we're going to do is go over the objectives of the lab. We have two objectives. The first one is going to be to establish which controller you're going to be using for your system. You're going to be choosing between P only, PI, or PID controller, and you're going to be establishing that based on multiple trials ran once with each controller and picking which one responds best to a change in your system. The second objective we're going to have is once you establish what your controller is, you're going to be figuring out how to tune the parameters to an optimum level. You're going to be doing that by running multiple trials at first with tuning parameters based on heuristics that you calculated from a previous lab. And then afterwards, you're going to be adjusting those tuning parameters yourself in order to figure out the best response from your controller. So just a quick equipment overview. Each system contains a controller, a control valve, two tanks, and a sump pump. And your process variable, depending on which version of the experiment you're going to be doing, is going to be either the water level or your temperature. Your set points are going to be either level or temperature and can be put into the controller, which are going to manipulate the flow rate. In the level experiment, you're going to be changing the flow rate to adjust the water level on the top tank. In the heat exchanger version of the experiment, you're going to be adjusting flow rate into the heat exchanger and measuring the temperature of the exit stream of the heat exchanger. And which version of the lab you do will be dependent on whether or not your equipment is going to be working for that day.
All right, thank you very much, Ethan. I will now be going over the equipment recommendations and the procedure of this experiment. The equipment recommendations will vary depending on which of the systems you are using. You will either be using a water level system or a temperature system, and you will be measuring those variables respectively. For the heat exchanger system, you want to look at temperatures below 35 degrees Celsius. That includes your starting point and any adjustments that may be made to your starting point. This is because the heat exchanger itself can only go up to around 35 degrees Celsius. If you have temperatures above this, the change will be very slow when you go above it. And as you go lower than that, it tends to speed up, but it gives you inaccurate data. Luckily, the water level system does not have this issue, so you are allowed to do it at any point in your set parameters. You then want to make sure that the system itself is in the proper corrective action. For example, the heat exchanger needs to be a forward-acting system because as you adjust the temperature, you want to see the same change in the system itself. If you send it as reverse acting, again, it'll mess up your data. However, if you're in the level sensor, it is a reverse acting system, and therefore you need to make sure that it is in the reverse acting state. As for the procedure, the first thing that you need to do is make sure that you set it up to the proper parameters. That does mean, again, that it is either forward or reversing, or as well as that your valves are connected properly, the computer is reading, and that you are at your set point. Then from this set point, you will run a total of 3 experiments, one for P, one for PI, and one for PID. Then, using these experiments, you will determine which of the 3 is the best experiment to use for your later data trials. Once you have determined which of the 3 you will use, you will adjust parameters such as Kc, Ti, and Td to determine the proper reaction rate of this system. As you get closer and closer to the system, you will need to repeat this process multiple times, which isn't that bad. And if you do it at the correct parameters, will be rather quick. You will then take all the data from the final experiment where you are comfortable with the response of the system and export this data for analysis. You can use this data to determine how close of a fit your system was, as well as seeing if you can adjust it further in the future. From here, Daniel will be taking over, so thank you very much.
Hi, my name is Daniel, and I'm going to talk to you guys a little bit about data collection and then some recommendations for the overall experiment. So hopefully you guys don't go through too many headaches while you're actually in the lab. First off, with some data, you're going to have a lot of raw data. There's many Excel files for all the different tuning heuristics that you're going to use. So you're going to want to keep track of those. There's going to be a bunch. It's not just one like the dynamic modeling lab, but it is similar in that you do export your data in a similar way and you get it on your flash drive so you can later compare all of your different tuning parameters. But make sure that with all these parameters, you're going to get a bunch of different heuristics with parameters. Make sure to mark down, this is this heuristic, this is this heuristic with the Excel files, because if you don't, you'll just have a bunch of Excel files with weird names that you have no idea what's going on with them. So just be careful about that, and you can obviously go on later and compare them graphically or however you want to do it, but just make sure you're keeping track. Next, I'll talk a little bit about the experiment recommendations overall, just so you guys don't pull your hair out while you're in the lab or get stuck in the lab for 3 hours or have to go back. Do a practice run before you're actually doing your experiment and recording stuff. This is going to help you. It just gives you a feel for the response time of the system of that day, and it helps to make sure that your step changes are reasonable. In our experiment, our step change wasn't reasonable. We were just kind of goofed, and we were in the lab for quite some time because that step change was not realistic for our system. There was a cap on it. So just make sure that everything is going how you think it's supposed to go with your step changes and the time that you're waiting for your system to reach equilibrium again. And speaking about equilibrium, wait for that system to actually reach equilibrium in your practice phase. See what that looks like. And there's most likely going to be oscillations with this. That's okay, more so in the heat exchanger system than the closed tank drainage system. Again, that's okay. It's not a big deal. Our equipment is not perfect, but just try to get a feel for when that equilibrium is reached so you can, use your time most efficiently in the lab and know when a trial has ended.
Lab safety requirements vary depending on which system is used. Generally, the equipment used in these experiments is very safe. However, anyone participating in the lab must take some standard precautions. For example, safety goggles must be worn at all times, and any surface which may be hot must be approached carefully. While using the heat exchanger, it is important to monitor the operating temperature to ensure that the machine does not overheat. Excessive heat is an indication that there is a larger problem with the equipment, and further operation could lead to a more dramatic breakdown of the system. Water spillage is also a concern. Inadvertent water leakage can lead to inaccurate results and create a trip hazard for anyone operating in the area. Be sure to have towels on hand to clean up any mess and have caution signs available to make everyone aware of the hazard. Lastly, good luck and enjoy your time in the lab. Thank you.